All right, so here we go. So, like I said, we need to talk today about rotational inertia, and specifically we're going to use it to talk about rotational kinetic energy. Okay? So, that's sort of what today is going to be about. All right? So, oops, there's a drawing left from yesterday. All right, so I would like you to imagine this 70-gram meter stick, 70-gram meter stick, sliding along a frictionless surface at 5 meters a second. Are you doing it?
Yes.
Okay. Because it's moving, it's got kinetic energy, right? And we ought to be able to calculate the kinetic energy, right? So I know this is silly, bear with me, let's do it, all right? So our kinetic energy is going to be 1/2 the mass of the meter stick times the velocity, which is 5 meters per second. Don't forget to square it, right? So we're going to get whatever 25 times 0.035 is. And I did not do that when I wrote up my notes, so I'm going to do this. 25 times 0.035, so you get 0.875 joules, right? So that energy is a result of energy in motion, right? Okay, sometimes energy is defined as the ability to do work, right? So the idea is if this thing was sliding along and it bumped into something, it could do work on that object, right? Cool? All right, so kinetic energy. Because we've got mass in motion, it's got kinetic energy, right? Now, suppose that instead of, oh shoot, and there's not a typo here, but I changed the way I wanted to do these notes. So let's suppose instead of the meter stick just moving along, let's suppose it was rotating. And in your notes it says around to the end. I want to change that. Let's have it rotate around its center. So you can squeeze that in there. So now what we're going to do is instead of having the meter stick moving, we're going to have it rotating around its center. Okay? Good? All right. So the issue there is if this is spinning around its center, the velocity of different points is different, right? Like the points at the outer edge have a higher velocity, right? Does that make sense? And the points at the center really don't have any, right? Because they're at a radius of 0, their velocity is 0, right? They're not moving. Okay? So, what we would have to do is we'd have to imagine this thing as the sum of a whole bunch of particles, right? Okay? And so the kinetic energy then would be the sum of the kinetic energies of all of the particles that make this thing up. Follow? Okay? So that would be the sum of 1/2 all of your masses, individual particle masses added up, times each of their individual velocities squared, right? Okay? So, but notice, one of the things we learned the other day was that V is omega times R. And since we're talking about rotating this thing, it's natural to talk about angular velocity, right? So my VI squared becomes omega times RI squared, right? Follow? It's just a simple substitution. I replaced VI with omega times RI. In other words, if I want to look at this particle, I'm going to multiply the angular velocity of the meter stick by this radius, and that would give me the velocity of that particle, right? Okay? So you can rearrange stuff. You can pull the 1/2 out, and you get this, 1/2 of this mess times omega squared. So, but notice, this mass and radius, that's a property of the object. This meter stick, as soon as I decide, all right, I'm going to pivot my meter stick around the center, those masses and those radiuses are predetermined, right? Because that's going to be determined by the shape of the meter stick, right? Okay? So we give this quantity here, the sum of the masses times their radii squared. For the meter stick, we give that a name. And that name is rotational inertia. Sometimes it's called moment of inertia, although I'm seeing that less and less. Okay, it seems like rotational inertia is becoming the more common term. But depending on how old your physics professor is when you get to college, you may hear them call it moment of inertia. Okay? So to calculate the rotational inertia of an object, and I'm going to say this a little silly, you simply sum up all of the masses that make up the object and multiply it by the radius squared. Okay? And then what that means is our kinetic energy is 1/2 of this I times omega squared.
Wait, is the sum only applying to masses?
Yes, but so there's almost an infinite number of masses, right?
Yeah.
So when I said you simply add this up, it's not really a simple thing, right? Because there's virtually an infinite number of particles that make this thing up, right? It's not infinite, but you know, it's certainly a very, 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 very large number, right? Follow? So then the obvious question is, all right, great. Well, how do I do that? How do I take this meter stick and divide it up into a, you know, a giant number of tiny masses and account for all of their masses and all of their radii? Yeah. Anytime you see an almost infinite sum, that should make you think of integration. Okay? So, here's the deal. Once you know the rotational inertia of an object, calculating the, I'm going to call this Kr, as in rotational kinetic energy, okay, because that's what we're talking about now, right? The kinetic energy of an object that's rotating. Okay? So once you know what this I is, calculating this rotational kinetic energy is easy, right? It's just 1/2 times whatever your I is, times your angular velocity squared, right? So it's very similar to 1/2 mv squared, except we're dealing with rotational quantities, right? Okay? But so then the question becomes, how do we find out? All right? So, here's the deal. Somewhere I have a water. So in the corresponding linear kinetic energy equation, it's this. 1/2 mv squared, right? And m we would call inertia, right? So in simple words, you guys, what is inertia? What's true about an object that has more inertia? It has more mass. It's more resistant, not to motion, but more resistant to a change in motion, right? An object that has more mass, an object with more inertia, will be more resistant to a change in motion, right? Okay, so that means that if I've got an empty shopping cart and a full shopping cart, and I push them with the same force, the full shopping cart has more inertia, more mass, therefore it's going to accelerate less, right? Good? All right? So, what determines the inertia of an object in a linear sense is the mass. Okay? What determines the inertia of an object in a rotational sense is not just the mass, but also where the mass is located. Okay? So, let's see what this next slide is. Okay, so I'll come back to this in a second. All right, so, I don't have enough for everybody, but you guys can finish here. Oh, sorry, I didn't mean to whip that at you. Oh no, I did a rotten job. I didn't count well. All right, so here's what I want you guys to do. And so I'm going to pass them around. So I just gave you a ruler with a weight at one end, right? Okay, so here's what I want you to do. I want you to, if you've got one in your hand right now, I want you to grab it and hold the weight end. And wiggle it. All right? Now, every time you stop at one end, you're causing it to accelerate, right? You're causing it to go from moving to not moving, right? And then when you go the other way, you're causing it to accelerate again, right? Okay, pretty easy to do, right? Okay, now, flip it around. And do it again. That's way harder, isn't it? Right? It's at least noticeably harder. All right? So have we changed the mass of the object at all? No. But by repositioning the mass, we've changed its rotational inertia. When it's this way, it's more resistant to a change in its rotation than it is when it's this way, it's less resistant to a change in motion. So this is a small rotational inertia. This is a big rotational inertia. All right? After you're done, share it with your neighbor. What's up, Ethan? Oh, hang on. Let's wait till you're ready. Yeah.
So we have got weight on either end.
Say that again. No, that's not correct because there's still mass out at the end. The only way we know inertia is if you had like a particle. No, they're both going, at any given instant, they're both going clockwise or counterclockwise. Okay, so it's angular velocity, not linear.
You know someone named Mickey?
No, I know, but he's apparently a, what's he, a hamster boy?
Yeah.
He's a little hamster boy, yeah, I saw that.
Are these stores?
No, they were runners, I found them. Yeah, does anybody know Nick Ryder?
They were.
No?
Yeah.
Alright. Yeah, I know, there's a bunch of them that say that. Do you have one too? The Nick Ryder's hamster boy one? So Nick Ryder, if you're out there, I'm sorry. Okay, alright, did everybody get a chance to play with those? Okay, cool. Does that, have you guys seen that before? Does that make sense to you? Okay, Ethan, you had started to ask a question.
What's the units of?
It's going to end up being kilograms times meters squared. Because the idea is each kilogram is going to be associated with some radius that gets squared. So both the mass of the object and its position from your axis of rotation could become a factor. Sorry. Just kilograms. So you'll see in a minute when we figure out our kinetic energy, when we use this. So technically, I guess, if you want to be super specific about it, it's kilogram meters squared per radian squared. Exactly. Yeah. And a lot of times those radians, like I say, they kind of magically appear and disappear. But so technically, that's what's going on there. Okay. I was going to say something else. Did I answer your question? Okay. All right. What was I going to say? I had something else I was going to say, and I lost track of it. I don't know. Okay. So it turns out that there's sort of a list of like common shapes whose rotational inertia we use. Okay. So when you're solving problems, very often you'll be using these. All right. So this is a list of some common shapes and their corresponding rotational inertias. Okay, I'll explain where they come from in a minute, but for now, just know that as you're doing the homework, if you're dealing with something that is long and skinny and rotating about the center, then this is the equation for the rotational inertia. It's 1/12 of the mass of the whole thing times the length squared. Okay? Whereas if you take that same long skinny rod and rotate it around its end, now the rotational inertia is 1/3 ml squared. More inertia, right? 1/3 is bigger than 1/12 because more of the mass is now farther away than if I pivot it about the middle. Follow? Good? All right. Now, it turns out that when you have something like this, the width this way doesn't matter. So you can see these two are the same equation, right? Okay, and the idea is that the width this way, you've still got the same sort of proportionally, you've got the same amount of mass at the same radius by making it wider, right? So the width doesn't matter. Okay, so let me finish my train of thought and then I'll get you in 1 second. So this would be like if you ever had something spinning this way, or this way, or this way. I think I just did the same thing twice, but you know what I mean, right? Okay. So this one I don't see come up a lot. This one, at least in my honors class, I use this all the time. Because instead of picturing it this way, if we picture it this way, it's a door. So like in my honors class, I do a lot of problems about, like pushing a door, that kind of thing. And this is the equation we use for that rotational inertia. Okay? Let me answer Ethan's question, and then I'll talk about Soda College. Ethan, what do you got? No. The AP curriculum says you need to be able to do some simple ones. Basically, the only ones I've ever seen come up are these two. So I'm going to show you how to do those today. It's not too bad. Yeah. No, you don't need to memorize them. There have been a couple, like I've seen a couple problems on AP tests where they've said like, a solid sphere rolls down a plane, da 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 da. If the rotational inertia of a solid sphere is, so they give you those values. Cool? And then the only exception would be, like I said, I think these ones you ought to be able to know how to do, and I'll show you how to do that today. And I think in the last 20 years, I think I've seen this one on one or, and I know at least one, maybe two of them. Yeah. Yeah, I think
Will these be on homework?
100%. Yeah, yeah, you're totally gonna need these on homework. Okay, everybody good? All right. So the second column is for round stuff. All right. So solid cylinder is the first one. Okay. And then solid sphere like a bowling ball, hollow sphere like a basketball. Cool? All right. So here's a real quick demo. This actually, I guess we can go ahead and show you that. All right. So if I take two carts that have the same mass and roll them down ramps at the same incline, the idea is both carts have the same mass, they have the same inertia. They're both being pulled down the ramp by the same gravitational parallel force, right? I said that weird, but you know what I mean, right? And so they should accelerate at basically the same rate, right? It doesn't work perfect because one of these carts doesn't roll quite as well, but more or less, they roll at about the same speed. Cool? Ish. It's not perfect, but here, let me try swapping it. Is it the cart or the track? I don't know. Try it again. Yeah, let's do the track. Okay, so anyway, good? All right. Now, it turns out that if you increase the mass of one of them, it still works, right? Because then you're doubling the force, and you double the mass, you still get the same acceleration, right? Okay, so I just doubled one of the masses, and it still works more or less, right? Okay? Now, these wheels are relatively small, and they simulate there being no friction, right? Okay? So, okay? Sorry. Okay, so these wheels simulate there being no friction, okay? So technically they're rolling, but these wheels have a very, very small mass compared to the overall mass. Okay, so that rotational kinetic energy is really basically insignificant. All right, so let's look at something where all of the motion is rolling. All right, so if I roll these two spheres, they have different rotational inertias, right? Yes, they're spheres. These two things, they have different rotational inertias, right? This one has a rotational inertia of 1/2 mr squared, and this one has a rotational inertia of mr squared. Okay, now this one's wood, this one's metal. Their masses are pretty close. They're not exactly the same, but the masses are very, very close to one another. Okay? Enough that, the difference is insignificant. Okay? So which one's going to have more rotational inertia? This one, right? Because it doesn't have the 1/2, right? This one would have half as much inertia, right? Conceptually, what's going on is this one has more mass farther out. This one is equivalent to having the mass farther out, right? Follow? So, since this one has more rotational inertia, that means it's more resistant to a change in motion. So when I roll it down the ramp, which one should go faster? Which one's easier to move? The wooden one, right? The solid one, right? So when I roll them, that one's way faster, right? Because it's got less inertia, and so it goes faster. Follow? They're both being accelerated down the ramp by basically the same force, because they have the same weight. But this one goes faster because it has less inertia. Good? Questions? Yeah.
Twice as fast as that.
It would be twice the acceleration. So yeah, at any given instant, it would be going twice the velocity. Yeah. Okay. So good. All right. Again, you don't need to memorize these, but that little table that's in your notes, you will need for the homework. Okay. So here we go. Any questions of what we got so far? All right. So now we got to talk about where these stupid things come from. I would be surprised if it showed up on the AP test, but if it does, I want you to have seen it at least once. Okay. Because it is in the curriculum. We are supposed to cover it. All right. So where do the equations come from? So, like we said before, this basically infinite sum can be written as an integral, right? Okay. So for our meter stick, the idea is it's more or less uniform, right? So remember when we did, Mr. Boda?
Yes.
Yeah. Boda. You said Mr., so I should write that. Okay, so remember when we did center of mass, how we talked about linear density? Kind of the same idea. This has a uniform linear density, right? More or less. Like any 1 centimeter has basically the same mass as any other 1 centimeter, right? So that gives us this relationship. That if I take the mass of the whole stick and divide it by the length of the whole stick, that's the same as if I split it up into small chunks. If I split it up into very small radius lengths and divide it by the mass of that little radius length, right? Hello? Okay. So if you rearrange this, if you multiply both sides by dr, it gives us this. Okay? So let's see if we can do this. What I want to do is I want to see if we can come up with this equation. All right, so we're rotating our our rod about the center, right? Okay, and so we're going to try to integrate and see if we can figure this out. So here's the deal. Here's the rod about the pivot point, the axis, whatever that little dotted line there is the axis, I guess. All right, it's got a length of L. Okay, and so to calculate the rotational inertia, I'm going to do this infinite sum. I'm going to integrate r squared with respect to the mass. Good? All right, so here we go, some calculus. So we want to integrate, or I is the integral of r squared with respect to the mass. So at this point, my integral is going from 0 mass until I get to the total mass. So here, capital M represents the total mass of the stick. Good? All right. But what I can do is I can replace dm with m over L dr. So this becomes the integral of r squared, and I'm going to replace dm with m over L dr. But now the bounds of my integration have changed because I'm no longer integrating with respect to mass. Now I'm integrating with respect to r. So if this is my pivot point, if this is my axis, the smallest radius I could have would be negative L over 2, and the biggest radius I could have would be positive L over 2. So now my bounds for integration become negative L over 2 to positive L over 2. Let me pause there for a minute. Does that make sense? All of our mass is located within a radius of somewhere between negative L over 2 and positive L over 2. So that's equivalent to integrating from a starting mass of 0 to an ending mass of the whole thing. Cool? Okay, cool. So from here, this actually isn't too bad. Stored. All right, so first of all, this m over L is a constant, right? Is the mass of the stick going to change? No. Does its length change? No. So I'm going to pull that m over L out. So this gives me m over L times the integral from negative L over 2 to positive L over 2 of r squared dr. So if you ignore the m over L, that's an easy integral to do, right? Like that's like probably one of the first integrals you guys did in calc, right? So this becomes m over L times, what's the integral of r squared? 1/3 r cubed. Oops. Finger didn't listen to me. All right, and then I want to evaluate it at L over 2 and negative L over 2, right? Good? Is this the notation you guys use in algebra, or in calculus, the vertical line?
Yeah.
Cool. Okay. Oh, sorry, these are L over 2, not 42. Sorry, those are L over 2. Sorry for my crappy handwriting. Okay, so let's plug this in. I'm going to be a little more detailed than you probably need, but I just want to make sure everybody follows the steps. So this is m over L times 1/3 of L over 2 cubed minus 1/3 of negative L over 2 cubed. Follow? All right, so what happens when you cube a negative? You get a negative. So I'm going to get minus a negative. This is going to be plus, right? So I'm going to have m over L times 1/3 of L cubed over 8, right? 2 cubed is 8, plus 1/3 of L cubed over 8. Cool? So 1/3 of something plus 1/3 of something is 2/3 of something. So I've got 2/3 of L cubed over 8. That's 2/24 of L over 8, which is 1/12. Okay, so this is m over L times 2/3 L cubed over 8. We'll do that. It's probably instead of doing too many algebra steps at once. Follow? 1/3 plus 1/3 is 2/3, right? Okay. So let's see, we can cancel some stuff out here. Let's see. And L cancels, and this becomes L squared. 2 and 8 cancels, becomes a 4. So I've got m L squared over 12. Which is exactly what we were supposed to get, right? That's 1/12 times L squared. Where is R? So it varies. So each point has a different R. Okay? So if I pick an arbitrary point here, then R would be this distance. It's the distance from your axis to wherever that point is. Good? And then going this way would be negative. Cool? Sorry if I didn't make that explicit. Cool, you guys, or no? All right, cool. So that is how those are calculated. Now, some of the other ones get a little bit ugly, like doing the sphere. There's a couple ways of doing it. A lot of times I've seen it done using a double integral. So, you know, whatever. That's more math than it is physics. But okay. Now, oh, blank page. There you go. All right. So we just learned this, right? Now, what we need to learn is what's called the parallel axis theorem. And I realized when I went through my notes again today, I didn't do a great job explaining what these things are. Okay? But so here's what the parallel axis theorem does. All right? The parallel axis theorem allows you to, so we just figured out the rotational inertia of this meter stick about this point, right? Okay? And notice that's the center of mass of the meter stick, isn't it? Okay? So if you know that, if you know the rotational inertia of an object about its center of mass, then you can find its rotational inertia about any parallel axis. So I can scoop my hand over 20 centimeters and find the new rotational inertia using the parallel axis theorem. Okay? But it's got to be parallel. So like, you know, this and then doing this is not the same thing. Now my axis isn't parallel. You know what I mean? Because now my axis runs up and down instead of this way. Follow? Okay? So in this expression up here, ICOM is the rotational inertia about the center of mass. Okay? So it's got to be about the center of mass of the object. Okay? So if I knew the rotational inertia around this point, the parallel axis theorem doesn't help me any because this isn't the center of mass. Follow? Okay. Now h is it's how far the axis of rotation gets moved. All right. So the idea is it's easiest to rotate an object about its center of mass. Okay? And then the farther away you move your pivot point from your center of mass, the more rotational inertia it has. Okay? So if I wanted to rotate it about this point, but you get the idea, then that's a large amount of rotational inertia because I've moved my axis a great distance. Follow? So I don't know why they use H for that, but that's what the book uses. All right? There is, if you want to see it in your book, there is a proof for where this comes from. You're welcome to look at it. It's just a little bit of calculus. I didn't see the value in doing it. Okay, so I hope that's okay. All right, so it says, so we could, if we wanted to, find the, oh shoot, I did a dumb thing. All right, so in a minute, we're going to find the kinetic energy of the meter stick rotated around the end. Okay, I realized I forgot to do something on the last slide. This is why I had the blank slide. So a minute ago, I went through and showed you guys how to calculate the rotational inertia of the meter stick, right? All right, the reason that we did all that was so that we could find its kinetic energy when I rotate it like this, right? Like that was the original question. It's up at the top of the page up here. I don't know, this must have been on the previous slide. Yeah, what if we rotated the meter stick around its center at 5 radians per second squared? Okay, so let's take a second and find that kinetic energy, and then we'll move on to the other example. All right, are we okay? I'm sorry, I skipped that. Everybody okay? Everybody back on board? Okay. All right, is that the right one? Okay. All right. So, if our meter stick rotates about its center at 5 radians per second, then, well, here's what we know. We know the mass of the meter stick. I told you that before. It was 0.070 kilograms. I know the length of the meter stick is 1 meter, because it's a meter stick, and that's how meter sticks work. And I know that my angular velocity is 5 radians per second. So I can use this information here to find my I. It's just going to be 112 ml squared, right? Because that was the equation we came up with. So that's going to be 1/12 of 0.07 kilograms times 1 meter squared. And technically there's a per radians hidden in here. You could rewrite this instead of in terms of L, you could write it in terms of R, and it would end up being 1/3, half of the length. Never mind. Anyway, it works. So to figure this out, your I turns out to be, where did I put my notes? Those are dumb notes. What do we get? What do we get? What do we get? You get 0.0583 kilogram meters squared. Cool? So now we can find our kinetic energy rotationally, right? It's 1/2 I omega squared. So it's 1/2 0.0583 kilogram meters squared times 5 radians per second. Don't forget to square it. And that gives you 0.0729, and the units do work out. You get kilogram meters squared per second squared, which is joules. What's going on, Timo? After school? Sounds good. Or 7th hour. Which were you? Okay. Yeah, no worries. Yeah. It's just kilogram meters. Yeah, unfortunately, there's no nice way to write it with newtons or. I guess you could write it as Newton second squared if you wanted. No, wait, that wouldn't be right. Newton seconds, we can't because proof by induction is named that from my 10th grade math class.
Wait, what?
So you know when you prove something by induction? So have you guys ever learned proof by induction?
I think
So,
so.
One of the four.
No, so proof by induction is a way that you prove like an infinite number of things. So you say, all right, let's suppose it works for I equals 1. Okay? And then you assume it works for k, and you prove that it works for k plus 1. Follow? So like if it works for 1, and you assume that it works for something and it works for the next one, then it'll work for everything, right? So that's proof by induction. And so when you prove something by induction, you say, so if it works for one and it works for a plus one, then it must work for all values, is what you're supposed to write at the end of proof by induction. But in my 10th grade math class, my teacher said, that's a pain in the ass to write that all out, so we'll just write hacker. So, no, we can't just call it a hacker. Okay. It's a long way around for a really crappy story. All right. Are we good with how we found this rotational kinetic energy? All right. Compare it to the kinetic energy of the meter stick just moving at 5 meters a second. All right. It's much smaller for 2 reasons. What was the kinetic energy before? It was like 0.8, right?
Oh, yeah.
Yeah. Am I right? Okay, cool. So it's smaller. So the reason it's smaller is a couple reasons. First of all, our units are different, right? We're talking about radians per second instead of meters per second, right? Okay. So that means that at its fastest, the outer edge is moving at 2.5 meters per second, right? 5 radians times 0.5 meters. Okay. So your velocity is less, and that's only the velocity of the outer points, right? The inner points have less velocity and therefore less kinetic energy. All right. Any questions on what we covered here? Okay, cool. So we are almost done here. This took longer than I thought it would, so I'm glad that I didn't add on more to the notes. Oops. All right, so now, what if our axis of rotation isn't at the center? What if the axis of rotation is at the end? Okay. Well, then we need to calculate our new rotational inertia, because the rotational inertia doesn't just depend on the object, it depends on the axis of rotation. So we use our parallel axis theorem, okay? So, if we rotate the meter stick about its end, I know, yeah. Sorry. I was just bringing us all back onto the same page. So here's what we know. We know that our rotational inertia about the center of mass was, what was it, 0.0583? Is that right? Kilogram meter squared? Good. All right, and then what would h be? If I go from rotating it here to rotating it here, what would h be? 0.5 meters, right? Because that's how far I moved my axis of rotation, right? So our new rotational inertia is going to be this. I of the center of mass plus mh squared. Which is 0.0583 repeating plus the mass is 0.07 kilograms. Our h is 0.5 meters. Don't forget to square it. So you get 0.0583 plus, what's a quarter of 0.07? There are my notes. That sounds about right to me. 0.0175 sounds good to me. So add this all up and you get, oh, well that's clearly not right. What did I do? Oh, I know why, because I did this differently on my notes. Is everything here right? Thank you. Oh, I'm missing a 0. It's 00583. Shoot, did I mess that up on the previous page? Darn it. Sorry, guys. Correction here. I'll do it in green with a big star. This should be 00583. Sorry. Missed a 0. All right, everybody good? Sorry about that. All right, so that then makes this work out. So now, 0, 0, 0, 0. So now when we add it up, you get 0.023 repeating kilogram meters squared. Good. So we could again find our rotational kinetic energy. I'll skip that because you guys could obviously do that now that we know what I is. And if our omega is still 5, you can still find it, right? So if you do that, you end up getting 0.292 joules. More rotational kinetic energy, right? Because you've got more rotational inertia at the same velocity. Good? All right, what do we got? We have 3 minutes here. All right, so, yeah.
So when people inertia is like what, like the inertia the object has like spinning?
Yeah, it's an object's resistance not to a change in motion, but it's a resistance to a change in rotation.
Okay.
Good? About a certain axis, yeah, and that's an important detail that I should not neglect. All right, so, yeah, Patrick.
How would you do it with the bowling ball?
How would you do it?
Yeah.
Same way. You'd find the rotational inertia about its center,
Yep.
and then however far you move it is just 10h squared. Add that up. Same exact thing. Yeah, so that parallel axis theorem works for any kind of shape. Once you know the rotational inertia about the center of mass, like the bowling ball about its center of mass, then you just do this to find, once you move it. Cool? All right. So real quick, I'm a little tight on time. When I did this last example in my notes, something that I guess you should be aware of is this equation here can be derived very easily by starting here and then just using the parallel axis theorem, right? Because all you're doing is starting here and then moving your axis over a distance of L over 2. So if you do 1/12 of ml squared plus m times half of L squared, it gives you 1/3 of ml squared. Okay? All right, and then I guess the one other thing that I should comment on is this. And it doesn't, for whatever reason, they never put it on equation sheets. So let's go back to that bowling ball example that Patrick was talking about. So imagine a bowling ball rotating about a thing that was like where your radius of rotation was super big. So in other words, the radius of the bowling ball itself is insignificant compared to this distance. All right? So basically we've got a particle rotating in a circle. All right? In that case, your rotational inertia is just the mass of the object times r squared. All right? And it turns out for this object, you can calculate either rotational kinetic energy or kinetic energy and you get the same value. You know what I mean? So you can treat this object as either a thing that's rotating or a thing that's moving, and either way you'll get the same amount of energy. Does that make sense? So you pick one or the other. It's not both. It wouldn't be like you add them together. Is that what you were going to ask?
No, I was gonna ask, so
And then I got
if you doubled the distance from the axis of rotation, it would like quadruple the inertial.
Correct. Correct. Yeah, and that's true with all of these, right? That, yeah. No.
So the income.
They're not different units. They still work out to joules.
One's kilograms and the other one's
Yeah. So the inertias are in different units, but when you multiply it by your velocity squared or angular velocity squared, right? So with rotational inertia, the meters are built into the inertia, but the velocity doesn't have meters in it. And then for linear, the mass doesn't have the meters, but the velocity does. Make sense? So yeah. So either way, your units work out to joules. Okay. Maybe I should actually do this calculation. Maybe we'll start with that tomorrow before we jump into the torque note, so you guys can see how this works. It sounds like there's a little uncertainty about it. So we'll start with that, and then tomorrow we're just doing torque. Okay? Okay. Cool. Good work, you guys.